Hello, my name is Violeta Menendez Gonzalez, and in this video I will talk about my paper, SVS Adversarial Refinement for Sparse View Synthesis. This work was carried on at the Center for Vision, Speech and Signal Processing at the University of Surrey, sponsored by BMVC Research and Development. Novel view synthesis is the problem of taking multiple images of a scene and trying to render an image from an unseen viewpoint. Previous approaches tackle the case when a dense set of images of a scene exists, or when few images cover the scene but they have significant overlap. Whenever a number of reference views is limited, or the target view diverges significantly from the reference views, these models struggle to reconstruct missing information and produce considerable artifacts. Key challenges of these approaches are inferring the scene's 3D structure given a restricted set of reference views, which are not necessarily coplanar with the target view. These approaches also tend to be very expensive, requiring a multitude of input views and very long per-scene optimization. We coined the term Sparse View Synthesis, which is a view synthesis problem where the number of reference views is limited and the baseline between the target and reference view is large. Under these conditions, current radiance field methods fail catastrophically due to inescapable artifacts such as 3D floating blobs, blurring, and structural duplication. This problem raises significant challenges with the inpainting of occluded and unseen parts of the scene. We also aim to learn a general model that can be applied to new unseen scenes without fine-tuning. We propose a fully differentiable approach that unifies adversarial training with radiance fields. Using multi-view synthesis techniques, this model is capable of generalizing to previously unseen scenes from just a sparse set of views. The first stage of our pipeline is a geometry volume generator. This allows the network to extract correlations between images, which can then be used to reason about geometry. The focus on image correlations as a mechanism for geometry extraction helps the network generalize to previously unseen scenes. The encoding volume is created at the reference view using multiple sweeping planes of warped source view 2D CNN features. These features are then aggregated into a variance-based cost volume, which is processed using a 3D CNN UNet network. Using a variance cost volume allows us to use an arbitrary number of input views and is consistent across any arrangement of these views. In the next stage, we use common ray marching and neural radiance field techniques to render our novel view. As well as giving the network the 3D location and viewing direction, we condition our radiance field on the extracted volume features and the original image color, which are then decoded into volume density and view-dependent radiance. The proposed approach is able to predict density based on the consistency of feature representations between views. Analyzing exactly which views correlate well for a given point can provide hints about occlusions. However, there is no simple mechanism to distinguish a region which has low correlation due to being empty and one with low correlation due to being occluded in all views. The prevalence of these fully occluded regions grows drastically as the number of input views is reduced, and leads traditional radiance field models to produce reconstructions full of unrealistic holes. To combat this, we couple the generation of these images with a discriminator network and undertake adversarial training. Adversarial training makes it possible to enforce realism in unobserved regions. Our patch-scan discriminator follows an L-scan approach which encourages the generator to produce more realistic results, able to fool the discriminator. Any holes in the reconstruction due to occlusions will provide obvious clues for the discriminator. Therefore, the generator can only succeed in its task if the holes are filled with hallucinated photorealistic content. The traditional approach to nerve training operates on random collections of unrelated rays per network update. Unfortunately, it is challenging to perform adversarial training without spatial structures. For this reason, we use a patch-based neural generator function. The use of a patch generator serves two additional purposes. Firstly, it exponentially increases the number of possible training examples, ensuring that the discriminator is not able to memorize the training dataset. Secondly, it greatly improves training efficiency as it can be expensive to repeatedly render entire images via the neural radiance field. We use a variable patch that scales with training time. This allows for a variable receptive field that learns independently of image resolution. Sparse view synthesis is an ill-defined problem. To be able to reconstruct a well-defined scene geometry, the predicted depth needs to be coherent with the image. We approach this issue by adding two depth regularizers. Firstly, we introduce a depth smoothness loss to encourage the network to generate continuous surfaces, similar to monocular depth estimation approaches. In addition, we want to get rid of other potential artifacts like 3D floaters. To achieve this, we add a distortion loss in our regularization, which helps the distribution function of the density along the rays approximate a delta function. We compare against several state-of-the-art models over two popular datasets, DTU and forward-facing. We can see our proposed approach performs similarly to RegNerve in terms of accuracy. This is despite the fact that RegNerve is trained in a scene-specific regime, while our approach is trained on unrelated scenes and then applied to a completely unknown scene at test time. We evaluate all models under the Sparse View Synthesis protocol, using 3 input views at test time. When comparing our technique to other scene-agnostic state-of-the-art approaches, we note that the simplistic peak signal-to-noise ratio and structural similarity accuracy metrics are relatively similar. However, we can see drastic improvements in the learned perceptual image patch similarity metric, which aims to capture human perception using deep features. Here are some visual results over the DTU dataset. Each column shows a different scene predicted under the Sparse View Synthesis evaluation protocol. We can observe fuzziness or smearing in the state-of-the-art predictions around object boundaries where occlusions occur. In contrast, our approach provides sharper edges as it realistically fills unobserved regions. Again, we can observe smearing artifacts in the state-of-the-art predictions from the forward-facing dataset, especially along the image borders. Additionally, we can observe halo or duplicated boundary anomalies in some of the scenes. These perceptually jarring artifacts are easily detected by our adversarial discriminator, so they do not occur in the predictions for our approach. In the ablation study, we proved the contribution of each main addition to the baseline. We can see the depth smoothness loss makes a small but noticeable difference across metrics. Interestingly, the distortion loss leads to a marginal decrease in PSNR and SSIM metrics, while it provides a more significant improvement in terms of LPIPs. This is expected as the distortion loss slightly limits the flexibility of the volumetric rendering by preventing smearing the scene across depths. However, this in turn removes floating blob artifacts and blurred scene depth when viewed from distant viewpoints. These artifacts have a significant impact in the overall perceptual quality of the rendered image and are vital for possible human-centric applications. Finally, the adversarial loss leads to significant improvements across all metrics, with the largest gains being with the LPIP score. This demonstrates that the integration of adversarial learning is vital for producing plausible renders for sparse view synthesis. To summarize, we propose a fully differentiable novel view synthesis model that generalizes to unseen scenes at test time and can successfully render new points of view using a sparse set of input views with large baseline changes. We show that our model outperforms state-of-the-art models by up to 60% using perceptual metrics. As the problem of sparse view synthesis is very difficult and ill-defined, our approach suffers from some lack of fidelity in areas that are completely occluded from all views, as well as training stability characteristic of adversarial training. In future, it might be possible to resolve this by reweighting the generative losses in different regions based on visibility or using alternative generative modeling techniques. Regardless, we hope the proposed approach is a major step towards achieving more extreme and sparse renderings. Thank you for listening. All the code used in this paper is available in this repository. You can send me any questions to my email address or find me at the BMVC in-person poster presentation.